Welcome to Chapter 5, Section 1, Intro to Normal Distributions and the Standard Normal Distribution. Okay, so first let's go over what are the properties of a normal distribution. So from Chapter 4, remember there's a difference between discrete and continuous random variables. Discrete means there's a finite number of possible values, it's countable. Continuous means it's an infinite number of possible values, and you can represent it on a number line. So the discrete example that we gave, it's something you can count, like the number of cars in the parking lot. That would be discrete. You can't have half a car. Continuous would be something like speed. You can go 135.5762 and continue to break it down miles per hour. So a continuous probability distribution is a probability distribution of continuous random variables. So everything that we dealt with last semester was discrete. Now we're going to look at what if there are continuous variables, meaning there's an infinite number of possible values. So last year we would make a chart where we would have our x and we would list all of our possible values. And then the second column would be our probability, our p of x, and we would put the probability of each of them. But this is going to be a little bit different because we're not going to be able to name all of the possible values because this is going to be continuous. So the first distribution we're going to look at is called the normal distribution. It's a continuous probability distribution for some random variable x. The graph is called a normal curve because it has these properties. The mean, the median, and the mode are all equal. So it makes it really simple. It's bell-shaped and it's symmetric around the mean. If you were to find the area under the curve, it would be 1. And it's going to approach, but it's never going to touch the x-axis, extending farther and farther away from the mean. On the next slide, we'll see a picture of this. But basically, if it's symmetric, that means you can fold it in half. The line where you can fold it in half is going to be that mean, and the area under that curve is going to be 1. So this would be an example of a normal distribution or a normal curve. So I see that this right here is my mean. Also, if I were to fold the graph down that line, I see that it's the same on both sides. It's symmetric. The whole area under this curve is going to be 1. Okay, and I can see that as I move 1 standard deviation, 2 standard deviation, 3 standard deviation to the right, 1 standard deviation, 2 standard deviation, 3 standard deviations to the left, I get closer and closer to that x-axis, but I'm never actually going to touch it. And it will continue on forever because, again, you have a continuous variable. These inflection points are always 1 standard deviation away. Oops, not our x. So our mean plus 1 standard deviation and our mean minus 1 standard deviation is going to give us what we call inflection points. So make sure that you have this graph copied down on your notes. I know I'm going kind of quickly. Feel free to pause if you need to copy anything. Okay, so remember, when we had probability distributions, we graphed them as histograms. Continuous probability distribution is going to be graphed using what we call a probability density function. Okay, so if I were to write out the probability density function, it looks like this. Which seems super complicated. So remember, the mean, the median, and the mode in the continuous probability distribution are all going to be the same. So whenever we graph it, that's going to be the point which our graph is symmetric around. So let's look at some more of these examples to see how we're going to do this. The mean and the standard deviation can be any positive number and we'll determine the shape of that curve, because like I said, the mean is the point where it's symmetric about. So depending on where your mean is, it's going to change the look of your graph. So the mean will give you the line of symmetry, and the standard deviation describes how spread out it is. Remember, the bigger the standard deviation, like in this case, the wider the graph is going to be. The smaller the standard deviation, the less spread out or the taller that graph is going to be. So if I look here in the first graph A, it gives me the mean is 3.5, and I see that line is right down there. So my inflection point would be at 3.5 plus 1.5, which is 5, and 3.5 minus 1.5, which is 2. So I can graph it by first plotting the mean and then the inflection points. Same with graph B. Graph B has the exact same mean, 3.5. So my line of symmetry is here, but my standard deviation is 0.7. 3.5 minus 0.7 plus 0.7 gives me my inflection points. So notice that A and B have the same mean, but they have different standard deviations. Therefore, their graphs look very different. In graph C, it has a totally different mean of 1.5, but it has a standard deviation of 0.7, which matches graph B. So you'll notice it's just as tall, but it's a little bit to the left, whereas the other one in graph B was a little bit to the right. So when you graph these, you're going to, 1, use the mean to figure out where your line of symmetry is going to be, and 2, use the standard deviation to figure out your inflection points. That's going to be much more simple than plugging into this equation. So let's look at page 237. The very bottom of the page, if you turn there, we have 3 different graphs. It says, consider the normal curves at the right. Which normal curve has the greatest mean? Well, remember, the mean is where it's symmetric. So if I look at the graphs of A and C, I see A and C are symmetric about the exact same mean, but I see B is a little bit to the right. It looks like for graph A, my mean is about 45. For graph B, my mean looks to be about 60. And for graph C, my mean looks the same as A, which is 45. So the one with the greatest is going to be graph B. Then it says, determine which normal curve is more spread out. Well, A looks to be the tallest and the skinniest. That's not very spread out. B also looks to be pretty tall and skinny. But if you look, graph C is shorter and fatter. So I would say graph C is more spread out. Therefore, it has the highest standard deviation. All right, if you turn to page 238, at the very bottom of the page, it says the scaled test scores for the New York State Grade 8 English Language Arts tests are normally distributed. The normal curve shown below represents this distribution. What was the mean test score? And then it says estimate the standard deviation. Well, if I'm looking at the mean, okay, it looks like it's just to the right of 650. And it looks like it counts by tens. I would say the mean is about 660. Now, the point of inflection should be 1 standard deviation away. So if I look, it looks like the graph starts to change direction maybe at 690, just before 700, that point of inflection. Well, from 660 to 690, there's 30. So let's go from 650 to the left 6:30 to about 6:20, and it looks like that's also where it changes direction. So I would say the standard deviation is about 30, because on your graph, fix that. If this is 660, it looks like it starts to change directions at about 690 and 630, which would be adding 30 and subtracting 30. Okay, so what about the standard normal distribution? This is the one we're going to use a lot this semester. This is a normal distribution, meaning it has all those same characteristics, but the mean is 0, which means the median is 0, which means the mode is 0. Super easy. And the standard deviation is always 1. Okay, again, super easy to add and subtract. So when you go 1 standard deviation away, you're at 1. When you go 2 standard deviations, you're at 2. When you go 3, you're at 3, because your mean is 0 and your standard deviation is 1. The horizontal scale of the graph is going to be made using z-scores, and z-scores will measure the position of how many standard deviations something is away from the mean. So you can take any set of information that's a normal distribution and you can change it to the standard normal distribution by changing it to a z-score. Z-score takes the value, subtracts the mean, and divides it by the standard deviation. When each data value of a normally distributed random variable x is transformed to a z-score using that equation, the result will give you the standard normal distribution. The area under that curve is going to be 1, the mean is going to be 0, the standard deviation is going to be 1. We can use the empirical rule, which we learned in chapter 3, to approximate the areas under the curve when the values of x were 3, -3, -2, -1, 0, 1, 2, and 3. Now what if we do if there's not those values? Remember the empirical rule was where we said we move 1 standard deviation, we are a certain percentage away. Where 2 standard deviations, we're another percentage of the data. Where 3 standard deviations, we're another percentage of the data. But what if we're not looking at exactly 1, 2, or 3? Here's what we're going to do. We're going to transform the x value to the z-score using the equation, and then you can use the standard normal table that is back in Appendix B. It's near where all of the tables we were using last semester are. So the cumulative area, or the area, is close to 0 if the z-score is close to -3.49. Well, if you think about this, the area under the curve is 1. When we go past -3 or above 3 standard deviations away, it gets very, very tiny, which means the area is going to be close to 0. As we move further and further along, what happens? The area increases. When you get to z being 0, which we said is our point of symmetry, it's our mean, we've reached half of the area. When we get close to 3, the area is almost exactly 1. Okay, so number 1 says find the area that goes with the z-score of -2.19. Number 2 says find the area of the z-score that goes with 2.17. So if you turn back to Appendix B, your standard normal table is, grab the exact page number for you, on page A16 and A17. So the z's are listed on the left-hand side. I'm going to go to -2.1 and then go over to 0.09 to find the area is 0.0143, which makes sense. It's close to 0 because it's not very far over. Now if we go to positive 2.17, I expect it to be much larger because it's much closer to positive 3. 0.9850. Again, much closer to 1 because my z-score is much closer to 3. Okay, so here's how you're going to find the area for each situation. Okay, number 1, if it asks you to the left of a z-score. Okay, that would be this direction. Well, if I know coloring from left to right, I should get closer and closer to 1. To the left, I can take it as is on the chart. But if they say to the right of a z-score, I'm looking at something like this, where everything to the right is shaded. Now I know going this way, everything should add up to 1. So to find my area, I'm going to do 1 minus whatever number I find on the table. And lastly, if they ask me for between two z's, that would look something like this. Okay, I would need to subtract the two values from the table. So let's do one example of each of these. The first one says find the area of the curve to the left of z equals negative 0.99. So if I were to draw this out on a graph, 0's here, negative 0.99, and I want everything to the left, so I'm going to shade to the left. Since it says to the left of that, I can just look at my table. So I go to A16 and A17 in my book. I look at negative 0.99, and I see the area is 0.1611, and I can leave it as is. The next one says to the right of z equals 1.06. So if I were to draw that out, 0 would be here, 1.06 somewhere over here, and it wants to the right of it. Well, my rule for the right is I take the area I find on the table, and I do 1 minus what I find on the table. So looking at the table, 1.06, I see is 0.8554. So when I subtract, this is my area. And then lastly, what if it says between? This one says between z equals negative 1.5 and z equals 1.25. Negative 1.5 is going to be over here, 1.25 over here. I'm looking for this. My rule with the between is to subtract the areas. Remember, we're doing area. If we're talking about area, I cannot get a negative number. So if you subtract in a way where you get a negative number, you've subtracted wrong, you need to switch the order. So when I look at the table, at negative 1.5, I see 0.0668. And at 1.25, I see 0.8944. I always want to do the bigger minus the smaller, because I cannot have a negative area. Does it make sense? And when I subtract those, I get my area. All right, so you have no homework for tonight. Your assignment for tomorrow will be to complete the 5.1 problems that I post on Google Classroom.